Hey everybody, this is Mr. Brooks. I'm gonna try to do a Punnett square for you guys. And as a note, I did these many, many years ago and have not done them in a while. But while I'm not teaching you, you're able to see someone else do it, and you're able to, kind of get an idea about how to approach it. So it starts out with talking about Gregory Mendel. You need to know what he did. He chose pea plants because he was a botanist and he had pea plants there. He was a monk, which means he lived at a monastery. That's where monks live. And if you live at a monastery, there's not a lot to do. I mean, you're sitting around praying and cleaning all day, so you got all this time. They're supported by the church, so it's not like they have jobs, but they don't have jobs. They're not going to starve to death. And Mendel grew pea plants because that's what he had. And pea plants have lots of traits that are easy to visually compare and classify. It's either it's tall or it's short, either it's wrinkled or it's smooth, either it's yellow or green. And so that's really the type of traits that you want to study. You don't want to study like, is it brown hair, blonde hair, dirty blonde hair, or some kind of blonde sometime and then not blonde, or red hair. So that's why pea plants turned out to be a great thing to demonstrate the probability, and that's what Punnett squares are. It shows the probability of traits being passed down. So it's not like, it's a science as to the probability, but it is still a probability as to what your kids get. So you can't tell for sure what the kid is going to have, but you can say it's this probability that the kid has it. And that also means you need to know, which you can work backwards to know, but without working backwards, you don't really know truly the genotype, right? So there's two words. There's genotype and phenotype. Genotype is the genes that you cannot see, right? You can't see the genes. And then I'm going to go back to that, but phenotype starts with pH, like physical starts with pH, like how you physically look. And phenotype is what you see. So you see my brown hair, my phenotype is brown hair. But what is my genotype? Well, genotypes can be either homozygous, homo meaning the same. So it could be like dominant brown, or it could be heterozygous, hetero meaning different. So heterozygous, my phenotype brown hair might be genotype heterozygous with a dominant and a recessive. And that assumes that brown hair is dominant because you can also be homozygous recessive, which means you have two small genes, right? Big letters are dominant and little letters are recessive. So we're gonna try to do this right here, and we'll pick blue because why not? Not text, drawing. So we gotta pick pink. Okay. All right. So it says SpongeBob SquarePants recently met Sponge Susie Roundpants at a dance, and of course they get together. SpongeBob is heterozygous. That means that SpongeBob is has the genotype with a dominant and a recessive, hetero meaning mixed or different. And Sponge Susie is round. Well, if she's round, that means that she cannot have the dominant round, because it later goes on to say that assume dominant is round or round is dominant. And so if she's round, I'm sorry, guys. It later goes on to say that square is dominant. And so if she's round, obviously she cannot have a dominant. So it has to be homozygous, meaning the same recessive. Okay, so make the Punnett square. Well, I'm going to put SpongeBob up top. I know SpongeBob is heterozygous. So that means he has a big gene and a small gene. That's his allele. And Sponge Susie, it says, is round, where square is dominant. So that means that she is homozygous recessive. So little r, big R, little r. SpongeBob up top, Sponge Susie on the bottom. And then you just put them in where they intersect. So like right here, you have a big R, little r. And then here you have a little r intersecting with this little r come across. and then this is the dad and the mom and the dad and the mom. Okay, so that is my Punnett square. Easy, put the dad up top, put the mom on the bottom. Doesn't matter, you can put the mom on top, dad on the bottom. But what does it mean? So it says, let's see, list all possible genotypes. The genotypes would be this, right? It would be R, of course, big R, little r, and then recessive, recessive. So this would be heterozygous. The offspring could only be heterozygous or um, recessive homozygous, homozygous recessive. That's it. What are the chances of the child with square shape? Square is expressed with the big R, and so that is 2 out of 4 has the big, and that's 50%, right? 2 out of 4 is 2 over 4, which is 0.5, which is 50%. And so these are, let's see, this would be the genotype, and this would be the phenotype, right? Because this is talking about the genetics, which you can't see, and this is talking about what are the chances of the child being square? Well, square is the physical, what you can see, so that's phenotype. What are the chances of it being round? 2 out of 4. And obviously, like if this is 50, this has to be 50, right? And if this was 75, this would be 25. I mean, there's a little bit, you can math it out, right? All right, so let's do another one. Patrick met Patty at the dance. This dance is getting everybody together. Both of them are heterozygous for their pink body color, which is dominant over yellow body color. Create a Punnett square to show the possibilities that would result if Patrick and Patty had children. So we're using the letter B. Pink is for B, and both of them are hetero. So we have a big and a little because it's hetero, and it's pink because if they're hetero, they have a big one, a big gene, and that big gene expresses right? So if you have one big, even if you're heterozygous and you have a big and a little, that big one is what expresses. You'll never have the small one express. So that means that it's big B, big B, little b. Patrick, Patty, or Patty and Patrick, they're both the same. So now we're going to fill in. This would be big B, because that's where they intersect. This would be big B from Patty and little b from Patrick. This would be big B from Patrick, little b from Patty, and looks like it's little b, little b. Okay. All right. So list all the possible genotype and phenotype. So the genotype would be, well, we have a big B, and that would be 1/4. And that would big B, little b, that would be 50%. And we have little b, that would be 1/4. Okay. So this is the genotypes right there. You should know, 25%, 50%, 25%. Of course, that adds up to 100%. And you should know that this is homozygous, heterozygous, homozygous. Okay. What are the chances of the child with a pink body? Well, pink is dominant. It says pink is dominant. So this one would have a pink body. This one would have a pink body. This would be 3 out of 4. 3 out of 4 is 75%. And what are the chances of the child with a yellow body? Well, this double recessive, homozygous recessive right here, does not have the large gene that would express itself, and so it would be 1/4. Now look, if you use 3 out of the 4, then the other one has to be 1 out of 4, right? Or 25%, right? Okay, so that's how to do a Punnett square and how to use it. Creating a Punnett square, you can see the genotypes and phenotypes of the offspring. And again, this tells you a probability of what's going to happen. So you can never be 100% sure. Um, but if you're using, like, obviously with human babies, humans don't have a large humans don't have a lot of children at once, but if you are, cultivating if you're breeding pea plants, then you can breed, like, hundreds or I don't know about thousands, but certainly hundreds of pea plants off of a mom and a dad, right? You take the pollen off and spread it, and you can literally do that for hundreds. Um, I don't know, how many seeds do peas have? At least dozens, at least dozens. So you can have a large sample. So, let's say you got 100, let's say you just got 100, you know, offspring off of a daddy pea plant and a mommy pea plant, then out of that 100, you could tell, like, if we knew the father and we knew the mom, 75 of those 100 would be pink, and the other, 25% would be white or whatever it is, yellow and green or, um, so if you were to breed let's say you didn't know, let's say you didn't know the ancestry of the seeds you're working with, but you raise a mommy and a daddy pea plant. Um, and then you take the pollen and breed the pea plant and you got 100 plants out of it and you got 75 green and 25 yellow, then you can work backwards and you can know that that both of them would have be heterozygous for that color, right? You would have to know what is dominant, is green dominant or is yellow dominant, but you can figure that out because 75% one is dominant, obviously. But yeah, I mean, you would be able to tell what the mom and dad are based on the results of the offspring, those observations. Okay. All right. Hopefully this helped. Um, have a good day.